I'm going to be talking about interest in generative models. This is a very boring title, so I have another title for you. How to use machine learning for mathematical modeling like a boss. Cool. So I'm going to suck the fun out of machine learning and tell you how to use it in mathematical modeling. And if you follow like trends in machine learning, you'll see two clear trends. First one is obsession with cats, as we saw earlier from Liliana's talk. We've got all these models that do different things with cat, like a cat generator fix-to-fix, a generator that generates cats from noise and stuff like that. And the other trend is, and this hype, you just hear a lot about the singularity and how AI will come soon and kill us all and all that. But none of this is relevant to us now. Because we want to use this for science. We want to use machine learning for science. Cool. So I'm going to talk about something called the implicit generative models, like my title says. And I picked this comic mainly because I didn't know what to put in between, and also it talks about like complicated names, and maybe implicit generative model is a complicated name. So what is an implicit generative model? It's a stochastic procedure that directly generates data. You can also think of it as a computer program that just takes some inputs and some parameters, and there's a stochastic procedure inside, and it spits out some outputs. So examples of these things are stuff like that, like climate simulations, galaxy formation simulations, epidemiological models like SAR model, population genetics models, and like stuff that we do in the complexity center. Right, and what we want to do is we want to learn the parameters of these models from we observe some real data set, and we want to kind of calibrate the model so that it sort of truly, as most as possible, convey what's the actual data says. So we have our real data, maybe this kind of blue distribution, and an implicitly the simulator and an implicitly defined model specifies the orange distribution, and we want to tweak these parameters so that these two distributions are as close as possible. So this looks a bit like hypothesis testing, and that's not coincidence because it's something like that. There are different ways to do this. I'm just going to talk about moment matching, or a version of moment matching. So stuff like these, like the density ratio is the GAN stuff that Liliana spoke about, but I'm not going to speak about these today. Right. So, the first thing that I want to speak about, well, the method that I want to speak about is called ABC, hence the, I don't know if you know this reference. Cool. So ABC stands for Approximate Bayesian Computation, and it uses Bayes' rule. Obviously, this badass person is, well, it's not actually Bayes, it's some people just said that this guy is Bayes, but it's not truly Bayes because he's from a different religious group, and people like that do not wear, they wear different clothes, but that's not important. What's important is this, the rule in the neuroscience. So, like Jim said, we have a prior, we have a likelihood function that we observe the data, then we adjust this prior according to what we observe, and we get a posterior. The trick with implicit generative models or simulators is we don't have, we can't write down the actual likelihood function, so we cannot calculate any of this, not even with the stuff that Jim mentioned, like variation inference and stuff like that. So what we do is ABC, which stands for Approximate Bayesian Computation. Cool. So this is Approximate Bayesian, well, this is the very simple version of Approximate Bayesian Computation, rejection sampler. We sample from, well, we specify a prior on our parameters first. We sample from that prior, plug that prior into the simulator, we get the output from the simulator, we compare that output to our real data, and if they're similar, then we store the value of the parameter that we sampled. If not, then we just throw it away. And doing this for lots and lots of iterations will give us a histogram over our parameter, and that would be our posterior. Great, but as you can see, this is a very stupid way to do this, because if we have a very large dimensional model, then it will just take, I don't know, a century or two to converge. So it's not very useful. A better way to do this is, well, the approximate Bayesian computation way, is instead of, so here we compare the real data to the simulated data, but with this one we compare a summary statistic of the real data with a summary statistic of the simulated data, and if they're somehow similar within some tolerance, if this d is a distance function, if they're within some form of tolerance, then we store the value of theta. If not, then we just discard it, and hopefully that will build us a posterior distribution. Cool, and this is kind of how it works. This is our prior. We sample from our priors, I don't know, n values of the parameter, and then we do a simulation on each one, and then we compare it with the real data. So this one and this one do not look like the real data. This one and this one look like the real data. So we store these, and then this will give us a posterior. So this is essentially just simulating Bayes' rule. This is what Bayes' rule is about. You have a prior, and then you kind of scale this prior according to your likelihood and your model evidence, and then you get a posterior. And we're doing that just computationally instead of analytically. Cool. The Batman reference. Cool. So I'm gonna wear my bat suit and give you an example. The SIR model that epidemiologists talk about a lot. So I did a stochastic SIR model, the simplest one possible, with two parameters. And this is my simulation. So I'll consider this the real data, and I want to learn these parameters. And I have a uniform prior on both parameters. So this is the real value of the parameters. And I do ABC. And then you can see the posterior kind of for R. So R, I'm guessing, is the infection rate, or sounds proxy to the infection rate. It kind of shrinks the interval in which the kind of prior is defined. But it's still fairly flat. We do a little bit better with alpha, which is the recovery rate. As you can see, it kind of disregards all this portion of the parameter space, and it kind of concentrates most of the mass on where the real value of the parameter is. So it works. Yay. Well, that's it. Cool. So break. Coffee.